This is a DC generator. Did you know that this has a DC generator in it? If you don't, then this is the right video for you because we will be talking about the working principle of a DC generator, graph and equations related to the DC generator, and the modifications and its effect on the DC generator.
Firstly, before we get into DC generators, we need to know what is electromagnetic induction. It can be defined as the production of electromotive force in a conductor where there is relative motion of the conductor across a magnetic field. And a simple example is moving a straight wire quickly across a magnetic field between two magnets. So what is a generator? An electrical generator is a machine which converts mechanical energy into electrical energy with the use of a generator. There are mainly two types of generators, DC and AC generator. This is Michael Faraday. He's the originator of Faraday's law, which states that the magnitude of EMF induced in a conductor is directly proportional to the rate at which the conductor cuts the magnetic field lines. Which basically means that if this magnet is pushed into the coil, the faster the magnet is pushed into the coil, the more EMF can be induced and also current can be induced, which also causes the deflection of the galvanometer. Lenz's law is all about opposing change. It states that the induced current will produce a magnetic flux that opposes the changing magnetic flux. In this diagram, when the magnet is being pushed into the coil experiences an increasing magnetic flux towards the right. And to oppose this, the coil will have an anti-clockwise induced current to produce a magnetic flux that is directed towards the left, because it does not like the change, so it will try to counteract it. Hence, the magnetic field produced by the induced current is also opposite to the motion of the magnet to, again, oppose the change.
Alright, now I'm going to talk about the Faraday's and Lenz's law. You know that when there is a change in magnetic flux, EMF is generated. This is Faraday's law, where EMF is directly proportional to the rate of change of flux. Now this EMF generated would induce a current through the coil, and we know that when there is a current, there is a magnetic field. This induced current would produce its own magnetic field that opposes the change in the flux that causes the induced current in the first place. This is Lenz's law. Now, in order to understand this law more clearly, let us look at this example here. Now, as you can see here, there is a bar magnet moving towards the solenoid, and we know that there is a presence of a magnetic field, which is downwards. Now, if you move the bar magnet closer to the solenoid, this will cause an increase in the magnetic flux linkage in the coil. Thus, the B field in the solenoid increases. Now this is where Lenz's law comes in and opposes the change in the flux that is increasing. Now how does it do so? We know that when there is a change in flux, the EMF is generated, which induces a current through the solenoid right here. Now this induced current will produce a magnetic field that opposes the change in flux. Now in this case, the B field is directed downwards. Now in order to fight it, like to push it up, the induced current will produce a magnetic field that is upwards. Now notice that this is quite similar to Newton's third law of motion, where every action is has an equal and opposite reaction. Now this difference in B field, where one is downwards and one is upwards, would cause a repulsion force. Okay, now that we know the direction of the B field induced by the current, we can determine the direction of the induced current based on the right-hand grip rule. Keep in mind that this is a solenoid, so therefore your thumb would be the B field and your finger would be the direction of the induced current. Now if you curl your finger with your thumb pointing upwards, you will get that the direction of the induced current is towards the right. Now this is Lenz's law. Now besides this, Lenz's law also obeys the law of conservation of energy. This is because if the flux continued to increase, the EMF increases and the induced current also increases, and this will cause a violation in energy. So therefore, Lenz's law plays an important role in opposing the change in flux, whether it is increasing or decreasing. Now because of these two laws, Faraday's and Lenz's law, this equation is deduced where EMF equals to negative n times the rate of change of flux, where the negative sign indicates Lenz's law and the rate of change of flux is Faraday's law. Now that we know the equation of the EMF, how do we calculate the magnetic flux?
Okay, magnetic flux. What is magnetic flux? Magnetic flux is basically BA cos theta. Magnetic flux density, however, can be imagined as the number of field lines per unit area, like this. Magnetic flux, however, can be imagined as the total magnetic field lines that pass through the surface area of A. Hence, magnetic flux equals to the magnetic field line per unit area times the area. The angle, however, the angle is calculated when the magnetic field between the magnetic field and the normal line. When the magnetic field is here, you can see that the angle is 0 and cos 0 is equals to 1, which gives you the maximum amount of magnetic flux. However, when the magnetic field is here, the angle is 90 and cos 90 gives you 0, which means that there would not be any cutting of magnetic field. Now for the EMF formula. This is the EMF formula. It looks complicated, and yes, it is complicated. But I'm going to explain briefly about this, and I hope you understand. So firstly, we need to understand that this formula exists because of the modifications made to the simple generator that I have shown previously. The number of poles and coils are added as it is a real-life generator. This is a DC generator. The number of poles here represents these poles. The number of conductor in armature represents this. So number of poles, there are 1, 2, 3, 4 poles. At the armature, you just calculate how many there are. The A, however, depends on the type of winding of the coil. These are some types of winding. As you can see that it's a bit different from this compared to this. So this is how a generator would look like with more than one coil. This diagram has 2 coils. It's a simple 2-coil DC generator. You can find it by this is 1 coil and this is the second coil.
A DC generator generates current which flows in one direction only. It is very similar to a DC motor, but generators are connected to a bulb or a resistor instead of a battery, because in motors they need the battery to provide current to make the coil rotate. But for generators, such as dynamo, it doesn't have a battery, so it rotates the coil to produce current in the circuit. There are 2 essential components of a DC generator. Firstly is the commutator, which changes the direction of current through the coil every half cycle to ensure the coil rotates in one direction continuously. Every half cycle essentially means that the rotation of 180 degrees. So let's say this coil would rotate in a clockwise direction. So every time it rotates in 180 degrees, the commutator would reverse the direction of current so that the direction of current would be maintained in these directions. So what this means is that it would ensure that the coil would not just rotate back into its original position, but instead produce a continuous cycle in a clockwise direction. In a carbon brush, it's used to transmit the electrical current from a static part to a rotating part of a generator. So how do DC generators generate current? We can use the principles of Fleming's right-hand rule to find the direction of induced current, so we can see the direction of electrical energy that will flow in this circuit or coil. Let's say for this coil, the magnetic field or B field will be towards the right from the permanent magnet's north pole to the south pole, and we will assume that this coil will rotate in a clockwise direction, and for it to rotate in a clockwise direction, there will be a motion of coil A upwards and the motion at coil B downwards for it to rotate in a clockwise direction. And what this means is that the motion, whether at A or B, upwards or downwards, will be perpendicular to the direction of B field. Hence, there will be induced current because there will be cutting of magnetic field lines. And after this coil rotates in a clockwise direction, 90 degrees, it will end up in this vertical position of the coil on the right. And let's say here, the coil will still want to rotate in a clockwise direction. And for it to do that, the motion at A will be towards the right, and the motion at B towards the left to produce a clockwise rotation. However, this does not produce induced current because the direction of motion is parallel to the direction of B field. Hence, there is no cutting of magnetic field lines, which does not produce induced current. So the coil would continue to rotate in clockwise direction to produce induced current because it's a generator. So how does this relate to the Faraday's and Lenz's law? According to Faraday's law, the induced EMF is directly proportional to the rate of change of magnetic flux in a coil. This means that the faster the coil rotates, the higher the rate of change of magnetic flux in the coil, which produces more EMF that will induce more current. So in simple terms, the coil rotates faster, producing more induced current. Next, according to Lenz's law, when the coil cuts the magnetic field line, there will be a current induced in the coil to produce a force that opposes the motion of the coil. So let's say at A, there will be a force that is downwards to oppose the motion of the coil, which is upwards. However, the value of this force is very small, hence it is negligible and will not affect the rotation of the coil, which is clockwise direction.
Alright, now I'm going to be talking about the relation between the magnetic flux versus time graph and EMF versus time graph. Now, as you can see here, there's a coil rotating in a magnetic field. And we know that based on Faraday's law, EMF equals to negative n times the rate of change of flux against time. This means that EMF equals to the negative of the gradient of the flux against time graph. So in order to get the EMF against time graph, you would have to draw the first graph, differentiate it into the second graph, and then reflect it to get the EMF against time graph. Now in order to draw the first graph, you have to draw the normal of each coil here, because we'll be using this equation, which is flux equals to VA cos theta, where theta equals to the angle between the normal and the magnetic field. So in the first coil, the normal is towards the right. In the second coil, the normal is downwards. In the third coil, the normal is to the left. The fourth coil, the normal is upwards. And the last one, which is similar to the first coil, it is to the right. Now the first coil, we know that the angle between the normal and the magnetic field equals to 0. And since cos 0 equals to 1, therefore we will get a maximum flux, which is around here. And in the second coil, we know that the angle between the normal and the magnetic field is 90 degrees. And since cos 90 degrees equals to 0, therefore we'll get 0 flux. And the third coil, you know that the angle between the normal and the magnetic field equals to 180 degrees. And since cos 180 equals to -1, therefore we will get a negative maximum flux, which is below the graph. Now the fourth coil, the angle between the normal and the magnetic field equals to 90 degrees, so therefore there will be 0 flux. And the last coil is similar to the first coil, so therefore we'll get a maximum flux. And right before the first coil, we'll assume that there is another coil which has a normal that is perpendicular to the magnetic field, so therefore the flux will be 0. Now if we join all the plots together, all the points together, you will get a sine graph. So now to draw the second graph, which is the rate of change of flux against time graph, we would just have to differentiate the first graph. And we know that the derivative of the sine graph is the cos graph, so therefore we'll get a cos graph. And you can also see it by drawing the gradient of the first graph, let's say at this point here. And since the gradient is equals to 0, therefore we will get x equals to 0 here. And then at this point, the gradient is positive, so therefore we will get a positive x value. And then in the this point here, you know that the gradient is negative, therefore we will get a negative x value. So now that we've got the rate of change of flux in time graph, we can get the EMF against time graph by reflecting it, because of the EMF equation. So if we reflect the graph, we get a graph like this. Now if we do it through equations and we differentiate the sine graph, we will get that d flux over dt equals to cos theta, and which is this graph here. And if we substitute this equation into the EMF equation, we would get that the EMF equals to negative cos theta. So the relation between the flux against time graph and the EMF against time graph is just the negative gradient of the flux against time graph. However, since this is a DC generator, therefore split ring commutators are used, which rectify alternating current to produce current in one direction, which is direct current. Therefore, you'll get a graph like this. But the direct current produced by a single coil is pulsating, therefore it is unsuitable. So practical generators have many coils and commutator segments, which would produce a voltage that pulsates very little. We will discuss the effects of adding more coils to a DC generator and the EMF produced in the next slide.
So I'll be doing a short explanation on the EMF produced by 2 or more coils in a DC generator. The effects of an additional coil may be illustrated by the addition of a second coil to the armature. The commutator must now be divided into 4 parts since there are 4 coil ends. The coil is rotated in a clockwise direction from the position shown. The voltage induced in coil A decreases for the next 90 degrees of rotation from a voltage of maximum to 0. The voltage induced in coil B increases from 0 to maximum at the same time. Since there are 4 segments in the commutator, a new segment passes each brush every 90 degrees instead of every 180. This allows the brush to switch from coil A to coil B at the instant voltage in the two coils. The brush remains in contact with the coil B as its induced voltage increases to maximum point B in the graph. It then increased to point A 90 degrees later. At this point, the brushes will contact the coil A again. So this is the graph shows the ripple effect of the voltage when two armature coils are used. Since there are now 4 commutator segments in the commutator, and since there are only 2 brushes, the voltage cannot fall any lower than point A. Therefore, the ripple is limited to the rise and fall between point A and B on the graph. By adding more armature coils, the ripple effect can be further reduced. Decreasing the ripple in this way increases the effective voltage of the output.
Some modifications made to DC generators. So the modifications include adding coils and poles, as I've said earlier. And as for this low noise, I think some of us can relate, as when we go to Pasar Malam, these kind of genset are considered as quiet generators. The weight of it depends on how much power the generator has, but over the years it has become lighter and lighter. The output is monitored by voltage regulators. Some recent technologies have also taken off their electrical parts, which makes it almost impossible to be damaged electrically. They also have thermal sensors to protect them from overheating. Okay, thank you. Yay!